Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. And today I wanted to go over the signal characteristics of an AC signal. So, understanding AC signal characteristics. So, some of the things that are very important to understand about this signal, the first thing is the amplitude. So, the amplitude is the peak values. So, in this case, you have 4 and it goes down to -4. So this would be considered your peak value. So you see it as VP. VP to peak would be 4 to -4, so that would be 8. So that would be another characteristic and it's denoted VPP, and that would be 8 volts. So the amplitude is half of that voltage of peak to peak. This becomes important when you do not have it centered around 0 in the middle. So you need to understand that voltage of peak to peak, and then the amplitude is half of that. So in this case, our amplitude is going to be that 4 amps. So the next thing to understand is the period. So the time period is from one peak or minimum to another one. So it is the distance between here and here, or you can say it's from the peak to the next peak. So it says that this is 0.5 milliseconds off of from 0. So this means that our period is going to be that whole distance of 5.5 minus 2. So looking at this, it's actually not quite 2. That bottom is about 2.4. And here I'm going to say it's 5.5. So the time period is going to be the distance between there. 5.5 minus 2.4 gives me 3.1 seconds. Actually, it's milliseconds. So the unit here is in milli. So milliseconds. So that is my time period. And to go from time period to calculate frequency, the relationship is 1 over the period, and milli is 10 to the minus 3. So that gives a value for the frequency of approximately 322.6 hertz. From frequency, we can translate into omega, which is angular frequency, 2 pi f, and we just multiply that out. And this is going to be in radians per second, and this is about 2027. And this is radians per second. The other thing we need to know is the phase shift. And a phase shift is in comparison to an input signal If this is our output signal, we can compare the two. So if it is not drawn on a graph, then we're assuming that the input starts at 0. And so this axis over here, we will say this is our 0 time in comparing to this signal. And we see that it is shifted at about 0.5 milliseconds. And so that comes as a peak right after the input. So if it is coming after the input, that's to the right of it on the scope, we would say that it lags the input and it's therefore going to be a negative phase shift. And the equation for the phase shift is a delta t. So that's the delta t, is that time difference between the peak of one input compared to my peak at my output. And that is over the time period t. And if we want to change this to and times 2 pi, so this is in radians, and if we want to change it to degrees, we do 180 degrees divided by pi. And in this case, we're going to take that 0.5 milliseconds. I'm going to cancel out the pi's, so I'm going to have 360 degrees over the 3.1 milliseconds. So this gives me a phase of 58 degrees. And again, it is lagging the input, so it's going to be a negative. So we add in a negative 58 degrees. So this would be the phase shift in radians or degrees, and we did it in degrees here. So now we can use all this information to actually write an equation for this I of t. So you use the amplitude, which in this case is 4, cosine, and it's omega, so you have to make sure that you're always in radians per second, unless you make sure to note that it's in frequency of hertz. And then we have the phase shift of minus 58 degrees. And that's in amps. So this would be our time domain expression for this signal. This concludes this example. Thank you for watching.